introduce these proceedings. This is a oral defense of a thesis for the degree of Master of Science from Michigan Tech by a student from the INVOGE program, Valeria Chigalas. She is completing a project about Pacaya volcano. She'll tell us the details about this, in which she had a long series of learning exercises which we tried to help her with. And today she will report about this. And I'd like to say a few words about the committee. First, I'm very pleased that we can make an exception in our procedure and we can have a co-advisor from France, from Clermont-Ferrand, Lucia Gurioli. We feel that her expertise is very important in this, and so I'm happy that through the procedures in INVOGE and Michigan Tech that we can do this, and it helps with the learning experience, and that's what we're about, to teach students and work with students and work together, and all these things are happening. So thank you all in INVOGE, and let's go on now with Valeria and her work. She will have there will be two parts of this defense proceeding. The first part is Valeria's presentation and questions from anyone for her. Then we'll take a short break and we'll have a closed session for the examination committee. The other people on the examination committee are Alessandro Tibaldi, who unfortunately is, I think, in bed today, but he's hopefully joining us, and Simon Karn, who's here sitting beside me in Michigan. Hello. So, hello, sir. Go ahead, Valeria.
Okay.
Yes.
Okay, so good morning at MTU and good afternoon in France and here in Milano. Today I'm going to present you my master research project entitled Fossil Bubbles in Porphyritic Basaltic Pyroclast produced by small and large strombolian eruption at Pacaya, Guatemala. Explosive volcanism is hazardous and impact on population, aviation system and infrastructure because of the production of large amount of pyroclasts. For this reason, the necessity to deeply understand the pyroclast formation mechanism arises. So I wanted to investigate it, since one of the main causes of pyroclast formation is explosive desiculation. I wanted to investigate if fossil bubbles preserve pre- and scene eruption processes and conditions occurring in the conduit. And to do so, I studied vesicles in ash and lapilli-sized tephra from Pacaya, Guatemala. Pacaya volcano is part of the Central America volcanic chain that is originated from the subduction of the Cocos Plate under the Caribbean Plate. And it is located 30 kilometers south of Guatemala City, the capital. The products at Pacaya, both tephra and lava effusion, show a monotonous basaltic trend, with the silica content between 50 to 52 weight%, magnesium oxide between 3 to 5 weight%, and alumina between 18 to 21 weight%. The mineral present are usually plagioclase, olivine, and iron and titanium oxides. The activity is mainly episodic, with a cycle of 100 to 300 years of eruption, followed by 300 to 500 years of repose. And the last and current cycle began in 1961, and since then Pacaya is one of the most active volcanoes in Guatemala, alternating Vulcanian, Strombolian, and effusive events. Freshfall material from the day of eruption, representing extremes of eruption intensity, were chosen from the sample archive of Pacaya fall pyroclasts collected by Bill Rose between 1965 and 2013. The first two eruption samples are on October 17, 1972 and August 12, 1977. These are characterized by a weak ashy explosion with fine ash reaching a few hundred meters, and the samples were collected less than 1 kilometer far from the event. The second two eruptions are on January 16, 2000 and May 27, 2010. And these are characterized by higher intensity events with Hawaiian-style fountaining reaching several hundreds of meters height. And in particular, for 2010, the convective eruption cloud reaches 21 kilometers. The sample from 2000 was collected less than 1 kilometer far from the event, while to obtain a similar granulometry, 2010 was collected 26 kilometers far from the event. So I made observation on loose pyroclast and on thin section. With loose pyroclast, I made grain size distribution from dry sieving, and I plotted the result with Gradistat by Plot and Pi 2001. Then I used an optical microscope to identify components such as juvenile, crystals, and lytics present. On polish and coating thin section, I run X-ray spectrometric analysis to obtain the chemistry of the ground mass classes and to compare them with the whole rock composition provided by literature and to classify them with the Keyware Magma software by Wallace 2009. And I also investigated the variation of viscosity with the differences in temperature and water content following Giordano et al. 2008. Then I used the NISCM to collect hundreds of images for each sample using backscattering signal. And on these images, I observed microtexture and I measured bubble size. To measure the vesicle diameter, I used INVOGE, which is a public domain Java-based image processing software that is provided with a macro editor. A macro is a written sequence of commands which allow you to automate long processes. So I wrote a macro that processes and analyzes all the images contained in a single folder per time. After setting a proper scale, according to the magnification used in the images, the macro is able to transform the grayscale images in binary and recognize and measure and outline bubbles. So the data that I obtained are areas and diameters for bubbles and a false color copies of all the images with the bubbles outlined and labeled. And when I found it necessary, I used the GIMP version 2.8, another kind of image processing software, to redraw bubble walls that resulted open and would have been difficult to recognize by INVOGE. And then I follow the stereology conversion method by Sajan and Prosevich, 1998. They provide a reliable conversion to infer 3D volumes starting from 2D measured areas of spherical objects. And to describe bubble size distribution, I calculated number densities, or number of bubble per cubic millimeter, and volume fraction for each geometric bin size. So in this slide, we have an overview of the 4 samples from pictures taken with an optical microscope. I observed juvenile pyroclasts, usually dark brown or black in color, vesiculated with sharp edges and sparkling surfaces. Then there are free crystals of plagioclase and olivine and pink reddish lytics, likely representing old basaltic pyroclasts from previous eruptions. 1972 is composed of fine ash-sized pyroclast, 85% juvenile, 15% lytics, with abundant free crystals of plagioclase and less abundant olivine. 1977 is composed of very fine ash-sized pyroclast, 95% juvenile, 5% lytics, with again abundant free crystals of plagioclase and less abundant olivine. 2000 is composed of lapilli-sized pyroclast, only juvenile and no free crystals are present. And 2010 is composed of ash-sized pyroclast, 97% juvenile. Here again, free crystals of plagioclase and less abundant olivine are present, but less abundant than 1972 and 1977. So from backscattering images, I observed microtexture. And in 1972, show usually pyroclasts with irregular and sharp edges. And bubbles are usually irregular and very small in size. And the ground mass is usually microlith rich, as you can see in the lower right image. when the ground mass is more glass-rich, we have pyroclasts a little bit more regular and smooth, and bubbles again more regular. 1977 show also pyroclasts with irregular and sharp edges and usually irregular bubbles. And again, the ground mass is usually more micro-rich than glass-rich. 2000 show instead pyroclasts with smooth edges and bubbles that are usually round and regular. But they can be elongated, like in the top right image, or irregular, like in the lower left image, when they interact or they are within a microphenocryst of plagioclase. The ground mass for 2000 is usually more glass-rich. 2010 show again pyroclasts with smooth edges. They can be irregular if the pyroclast is composed of large microphenocryst of plagioclase and olivine, like in the top left image. And bubble again are usually round and smooth, but they can be elongated or irregular when they interact with microphenocryst. In the lower images, we can see on the left a microlith-rich ground mass, and on the right a more common glass-rich ground mass for 2010. All the observations I made about microtexture are summarized in this table, and the main characteristics that we can observe are that pyroclasts with irregular edges are usually in 1972 and 1977, and these two samples have also the smaller microphenocryst. Plagioclase is the most abundant mineral present in all the four samples, and more in the 2000 and 2010 are usually more glass-rich, and bubble are more smooth and round. So I plotted the chemical analysis from the ground mass glasses and the whole rock composition on the total alkali silica diagram following DPS classification. What is clear are two main observations. The first is about glasses comparing to whole rock. The glasses result more evolved with the basaltic andesite trend, while the whole rock composition fall all into the basalt field. The second observation is about the date of eruption, since the oldest are always more evolved than the more recent one. I also investigate a likely range of viscosity following the model from Giordano et al. 2008. First, I observe what happened changing the temperature. And I see that increasing temperature, the viscosity decrease with an arbitrary amount of water, 2% in this case. Then, since at Pacaya gas emission are usually variable, I investigated how viscosity changed with the range of water content from 0 to 5%. And again, increasing water content decreased viscosity. The same trend is observable for all the four samples in both cases. Grain size distribution is plotted here with the particle diameter in microns on the x-axis and class weight percentage on the y-axis. From grain size distribution, we can classify 1972 as fine ash with a range diameter between 22 microns to 1 millimeter. 1977 is very fine ash with a range diameter of pyroclast between 10 to 410 microns. 2000 is classified as lapilli with a range diameter between 1 to 9 millimeter, and 2010 as hash with a range of diameter between 400 microns to 1 millimeter. Bubble size distribution are here expressed to compare on the left y-axis number density or number of bubbles per cubic millimeter of volume, and on the right y-axis volume fraction expressed in percentage, versus the vesicle size equivalent diameter in micron on the x-axis. This comparison shows immediately that number density and volume fraction are inversely related. In fact, we have that for the smaller, we have more numerous smaller bubbles than bigger ones that have larger volumes. The extremes here are shown by 1977 and 2000. In 1977, for the smallest bean size, we have the highest peak of number density and the lowest peak for volume fraction. While in 2000, we have the lowest peak for number density, and for larger bean size, we have the highest peaks of volume fraction. 2010 here should result in a value of number density that should be lower than 2000 since its intensity is higher. But I suggest that this is a likely effect of the difference granulometry of 2000. So using a finer fallout sample from 2000 would have resulted in a number density value between 1972 and 2010. In fact, these charts show also that number density in this case is inversely related to intensity of the eruption. So I'm aware that measuring 2D bubble areas to infer 3D volumes has a limitation. It assumes that bubbles are whole spherical and they do not present a preferred orientation. But our results look reliable and they are comparable with literature. And also, in less time than the other methodology, I was able to collect a statistically robust data set with at least 700 bubbles measured for each sample. So the preservation of bubble size and number density in pyroclast could reflect condition frozen at some point during eruption, where the cooling is marked, and a marked cooling increases the viscosity, which will freeze bubbles in place. Also, the loss of volatiles can increase viscosity. So it's likely that even without cooling, exsolution might freeze the bubbles in the melt. However, I think that it's more likely that the temperature effect, which is dominant during magma ascent, could be the cause of bubble preservation. So in this case, I investigated well-chosen sample from where style and rate of eruption are known, and what I found is that number density is inversely related to the intensity of the eruption. So it's interesting to try to understand what does an higher number density for lower intensity eruption reflect. It might reflect a substantial cooling before eruption, where freezing bubble size and higher number density at a pre-eruptive stage. And the cooling might reflect and might be consequence of an interaction with groundwater or hydrothermal water. Pacaya experienced 3 to 4 meters of rain per year, and it's also marked by eruption that drain shallow magma bodies that are just a few meters from the surface. So I suggest that this interaction might cool shallow dikes and seals and produce and induce fragmentation and so explosion in the volcano. Some of the pyroclasts from the lower intensity eruption here analyzed show a dictitaxitic texture, which usually is related to explosion and eruption triggered by groundwater interaction. But this hypothesis is only weakly supported by our result. So we can also make comparison between different volcanoes which has a similar style. For example, at Stromboli, Italy, Collò et al. 2010 also found that for high-intensity event, there is a big population of large bubbles and a smaller number density. They suggest that a density-driven convective magma column model, where a high concentration of volatiles will induce a high density contrast and viscosity condition boosting larger bubbles. Again on Stromboli, Bellian et al. 2010 investigate the role of crystallinity in driving explosive eruption. They have found that for high concentration of crystals in the melt, this concentration might control gas flux and bubble migration. So they show that with analog model, that large bubbles moving around crystals might deform and break up, splitting in smaller ones. So an enrichment in smaller bubble for them means probably and more possibly an interaction with this kind of mechanism instead of be related to nucleation rate. At Pacaya lavas, the crystallinity usually show a value around 45%, data from Morgan et al. 2013. And this leads to a possible complex and critical role of crystals in vesiculation dynamics. Genero et al. 2013 studied high-intensity event on Fuego, Guatemala, a volcano which behaved very similarly to Pacaya. And they found the vesicle size and void fraction that are comparable with our data on Pacaya. And he also found that for small family of vesicles, they have higher number density, and for large bubbles, they have smaller number density. The large mode is explained from them with bubbles nucleated and grow at greater depth by expansion and diffusion, while the smaller one should reflect late nucleation. For volcanoes with a different style, we have instead Stovall et al. 2011-2012, Carey et al. 2012-2013, which studied bubble size distribution from tephra at Kilauea, Hawaii. The first team found that they have higher number density for higher intensity event. And they suggest that higher fontaining episode might be associated to greater degrees of nucleation, which then drive higher ascent rate. This result is in contrast with what we have found at Pacaya. The second team worked instead on peculiar textures, possibly induced by rock fall within the conduit, which would cause a local pressure change and the nucleation of smaller bubbles around previous larger one. So in this case, the explosion and the eruption would be triggered by an external factor. In conclusion, the methodology here proposed is reliable, and I investigated samples from different intensity activity. And I found that for low-level eruption, we have fine-grained pyroclast with median diameters between 80 to 330 microns, more bubbles, 4,000 to 7,000 bubbles per cubic millimeter, and smaller, with peaks for 40 to 70 microns. And the vesicularity is usually lower, with 4 to 8%. While for the two high-energy eruption, we have median diameters of the pyroclast between 650 and 3,700 microns, and fewer bubbles, 1,000 to 3,500 bubbles per cubic millimeter, but they are larger, with peaks for 100 to 160 microns, and higher vesicularity, 11 to 26%. So the geochemistry and petrography do not vary at Pacaya, so the trap bubbles variability likely record variation in the gassing. So basaltic tephra record bubble data that could reflect eruptive style, and at Pacaya number density is inversely related to explosiveness. Thank you.
Very good. That completes your presentation, right?
Yeah.
Yeah. So let's start with questions from the people I see behind you in Italy. Do you have some questions for Valeria?
No, it seems that nobody has question.
Okay. Well, how about people behind me here? Ricardo, Bob. Okay. Benjamin?
What about Lucia?
No, first you. And
first
then,
me.
Well, I wanted to ask people that are not on the committee first.
Yeah, okay.
Be sure they have a chance.
I've got a really stupid question to start with. Why do you call them fossil bubbles?
Because they are bubbles preserved in pyroclast, so something that should record the condition that are not existing right now. So they are fossil. They record something old or older.
Okay, but all the bubbles are in the same state, so are all the bubbles fossils? Or only a population of them?
What do you mean?
Well, I mean, if you pick up a pyroclast, it's full of bubbles.
Yeah.
So are they all fossil bubbles?
Yes.
Yes. Okay. It's just, I was trying to think of bubbles and fossil bubbles and getting confused right from the start. But that's normal.
How about the ones in your beer?
Well, they will probably be just bubbles, Bill. Yeah. I've got another question as well, because I've looked at these samples with you. When we look at the first two eruptions, what you don't give in the conclusions is something that I always like, is some sort of idea about what was going on at the volcano at the time of eruption. So can you say for this number density and from the petrography, what type of eruption, what conditions were you expecting in the conduit for each type of eruption? Can you give two sides of the two sides of the types of eruptions?
Okay. So from the microtexture in particular, and the fact that 1972 and 1977 look more, for example, microliths rich, so might means that they had more time to crystallize, and so longer time of repose before actually be able to erupt. While in 2000 and 2010, they show a more glass rich, so might be more even fresh material coming from deeper and helping the eruption happening. And from the bubble size, what is clear is that there is a difference between the bubbles in 1972 and 1977 and in 2010 and 2000. And this is showing the number of the smaller one in the two weak eruption, while in the two more intense we have bigger bubbles, less in number. This is the main characteristic. So. Did I answer the question?
I think so.
Okay.
Yeah. Maybe it's time for the experts.
So, Bill, can we ask question now? Do we wait after?
If you want to, we used only 25 minutes, so we could go a little longer with the whole group. I think maybe as a committee we should think about general questions now and worry about more detailed issues during the closed session. Do you think that's a good idea?
Yes. Okay. So
go ahead.
Yeah, I just have a general question for the audience. And Valeria, you should help the audience to understand things better. Because when you show the table about the energy of the event, you put V equals 0. Now, for someone that is not a volcanologist, the first question is, how you can have an explosion with V equal 0? So can you explain the audience that is not volcanology the meaning of that?
Yeah. The V number is usually calculated, historically calculated, taking in consideration the amount of product erupted during the eruption. And so this doesn't take in consideration even like very small amount. Very small is very small amount of particles that are actually erupted. So the eruption is explosive, but it's not enough big to say that it was explosive. So there is a recent paper from Houghton et al. 2013, which they are trying to change this classification and introducing a more logarithmic scale for the explosivity intensity with numbers that are also negative. And
yes.
in this way, they are trying to actually better represent the range of explosiveness that we can have in a whole kind of eruption. So.
Yeah, thank you. Yes.
But for now, they are still with 0. So.
Yeah, but 0 doesn't mean that it's 0. It means that it's lower than 10 to 4 cubic meter, I think. I mean, it's a little amount, but it's important to take in consideration because there are a huge variation in intensity for this little amount that can come out from this mild explosive event. Good, thank you. Vale, thank you.
So I have a general question for you. Because I know that you used some methodology that came from concrete, observations of concrete. And so can you explain to the audience why observations that were designed for concrete actually give useful information for pyroclasts?
Yeah, so the macro that I wrote and modified was actually produced to analyze fly ash in concrete. So to analyze particles that are rounded, and so I could use the base of this process to try to find to measure bubbles in pyroclast. So that came.
So can you explain? Sorry, can you explain what fly ash is?
Okay. Sincerely, not.
I think it's a waste material that comes from silicates that are created in coal burning fires.
Okay.
And so it's a waste material from industrial processes that gets recycled in this case. But it has some similarity to pyroclasts.
Yeah.
I just wanted people to realize that interdisciplinary aspect, that you benefited from a lot of experience that comes from really a civil engineer, which is an interesting part of your work.
Yes, I would like to add that this process that Valeria did in making this macron and in making the automatic processing is the part that really fascinated me, because Valeria, I think, is one of the first that did that. When she came to Clermont, I have never studied ash before, and she came with this idea, and then together, but mostly Valeria, developed this method, and I think she found a very nice method to do this kind of study. And I think this is probably the most interesting part of the process. She did very, very well. So I'm glad that Michigan, she managed to do this integration with other disciplines that help her to define and improve this macro. I was very impressed by that. Thank you, Michigan.
Do you want a general question?
Yeah, sure. Hi, Valeria. I just wanted to ask a general question, which is, common to all volcanology topics really, is how do you think this information you've sort of discovered could be useful for volcanic hazard assessment? Do you think you've improved what we know about Pacaya and the way it erupts?
Yeah,
What's
I
the
think
practical
that
application?
I think it can be useful maybe to produce more data and more results from more samples, and maybe actually start making it continuously, like as taking more new samples and do it, and probably getting information about how Pacaya actually erupt. Maybe we can search for more data from bubble size distribution and even microtexture on this pyroclast, on ash actually, which is still new and quite complicated to interpret.
So it seems that the behavior of the volcano has changed, right, over time? Would you agree with that?
Yeah, a little bit. So there might be a reason, and this can be something to arrive to the answer.
Okay, thank you. I think you convinced the audience.
I hope so.
So one more question from me is, I was still thinking about the methodology, and I didn't see in your presentation a comparison of how many bubbles were examined And I know that some of the other studies of bubble size distributions report bubble numbers and some number of pyroclasts and so on. And so can you tell us, give us a comparison of the statistics that come from size distribution, because you were, I think, able to count quite a large number of bubbles compared to other methods. Is it possible to frame that more clearly and explain that to the group now?
Yes. So what I was able to do with the SEM was taking lots of images, hundreds of images for each sample, which allowed me to have a statistical number of bubbles counted for each sample, from at least 780 bubbles from 1977, if I remember right, and I counted for 4,000 bubbles. And these are huge statistical numbers. I compare it with the General et al. 2013. They use a different methodology, a new 3D methodology, and they count for 10 particles. They are able for each particle, I think for 10 particles, around 100 bubbles. So for each of 10 particles, for each of the samples that they study. And also because their methodology is long, needs more time to acquire the images properly. While with the ESCM, I was able really to, in a few hours of work, to collect a lot of images. That was I think, one of the best parts of the methodology here present.
And part of the reason must be the software that you use, which can be done quickly, at least in terms of human time. There must be some savings by using an automated software like that also.
Yeah, exactly, because I don't have to pass by, for example, Photoshop to make the images binary, but the ImageJ and the macro made them binary automatically, and it make it for hundreds of images at the same time. So in that also there is a saving time. For sure.
So again, for the audience, is there something that is transferable to another investigator, a software tool that would benefit them if they were interested in collecting bubble size distributions?
Yes, it's actually my macro is available on one of the MTU web pages, and it's available and everybody can use it. Also, ImageJ is the public domain, is downloadable for free, so everyone can do it. They just need an ACM.
And Valeria, can you use it for crystals or just for bubbles?
Well, for bubbles it's easier, but it can even work for crystals. But since in Ashley are very small, it's a bit difficult and complex. But I think we can even make it to work for crystals.
And just one quick question about the methodology that I'm very happy about, because I would like to export it here in Clermont, because I'm happy to work in 2D. And how much work you have to make by hand to make correction? A lot or just a little bit?
So I made correction with GIMP on the images when I found that, for example, the bubble walls open. So if there are a lot of bubble open, then you have to do quite a lot of manual work. And then just and then there is a manual checking of the data that you export from ImageJ in a spreadsheet. Since it might happen that ImageJ collected a void that is not a bubble, so I have to check if it takes the right one. But I think that for it, when you have, even with 4,000 bubbles counted, a couple of hours of work, I mean, it's 4,000 bubbles, so I think it's worth it.
The importance of automate a process and make it fast will answer also the question of Simon about the hazard. If we are able to make this kind of analysis fast, we can study the pyroclast almost in real time to answer the question, do we have variation, for example, with density in time, and what this variation is telling us? The system is getting more energetic or less. In your case, for example, it seems that denser clusters tend to characterize the less explosive explosion. Instead, the high vesiculated, but with low number of vesicles, tend to characterize more explosive eruption. If this is true, that can be a way to follow, and we can use it to help for the understanding of the explosion. And give a quantification. Like when we have an earthquake, we give, now we say, we give a scale. In this case, we can give a quantification of the explosivity of your event.
Yeah.
So I think this is the way, Simon. We are doing the same on Stromboli. We want to do the same at Piton della Furnese. So good job, Valeria. Good.
Thanks.
Yeah, good.
Okay, well, let's do our 5-minute break now and say goodbye to the audiences. We're glad that you came, and hope that you enjoyed this learning experience from Valeria. So, see you in 5 minutes.
Okay, so I have to be here, right?
Yeah. Yes, please. And we'll leave everything on because it's working now. And so we want to have it keep working after 5 minutes, but okay.
Bye, Valeria.
Bye. Bye.
Tell you that you have successfully passed this examination. We were all very happy with your presentation, and we also are very happy with the text that you sent, but we are all going to send you some comments.
Okay.
And we want you to react to these comments and to send them back to us so that you can submit it in time for the deadline during this semester, and according to the final oral exam procedures. And so it's a happy result. We are all happy to have worked with you. We think that you are a good student, and you take advice very well, even though sometimes we may not have been completely patient with you. You did very well, and we think you have a good future ahead of you, and we want to continue to help you with this. And so we'll try to give you suggestions that lead you in the direction of a publication from this result. And so it's a happy result for all of us. Thank you very much for working with us. We learned something, and we think it will lead to more students who are interested in tephra studies, and the difficult part is having advisors that are scattered all over the place. But hopefully, by doing this, we can do a better job because we have more experience we can translate to you. So that's my statement. Maybe Lucia and Simon would like to say something too. I don't know.
Yes, I would like to add that I'm very, very happy. It was a great occasion to work with Valeria. I learned from Valeria. Sorry, Valeria, for the first approach. I was quite sharp, but the results are great, so I'm very happy. You did a good job.
Thank you.
Hoping to see you doing a PhD, perhaps with us, with Michigan, I don't know.
Both.
Yeah, congratulations, Valeria.
Great.
Congratulations. Just wanted to say, sort of reiterate what everyone else said. Very nice, thorough piece of work. Definitely some publishable material. obviously I just came into this at quite a late stage as the committee member, but it's very interesting and definitely something to be built on as, if you're interested in a PhD. Definitely lots of future directions you can go in. But yeah, nice job and congratulations.
Thank you.
Wow.
One thing you could do with this work, and I just throw this out for you. This is not part of your assignment. This is for after December 16th. But after December 16th, you should take a glass of wine and sit with this glass of wine and think about your own research project which builds on this experience, because your work presents an opportunity for a new conception of what you can do with fossil bubbles or something related to fossil bubbles and pyroclastic mechanisms or volcanic mechanisms. And if you think about this, you might be able to find all by yourself a new idea for research. And so take this chance to do that and see what happens.
Okay.
Thank you for the experience.
Thank you very much.
Good.
Okay.
So, well, good evening, Milan. Good morning, Michigan.
Yeah.
Good evening.
Thanks for the nice. Yeah.
Thank you.
Bye-bye.
Okay.
Bye.
Bye, everyone. See you at San Francisco. Bill and Simon.
Yeah.
Yeah.
Yep.
Bye.
Safe travels.